Olá, gente. Bem-vindos nesta nova sala de seminários do Departamento de Raios Cósmicos e Cosmologia. Hoje temos a honra e o prazer de ter Jaki Noronha-Hostler. Ela
Giorgio, I think you're mute.
Hi. Thank you. I'm sorry. Yeah. Ok, desculpa, gente. Internet foi embora e isso aconteceu. I think you can share again. Para repetir, Jaki é de South Dakota, dos Estados Unidos. Fiz universidade em Berea College e depois fiz doutorado na Universidade de Frankfurt, no mesmo grupo onde eu fiz postdoc. Depois ela foi para a Columbia University em Nova York como Research Scientist. E depois ela foi para a IFUSP de São Paulo. Ela entende português bem, escolheu dar esse seminário em inglês, por uma pesquisa desse tipo de física inteiramente em inglês, mas para perguntas eu acho que não vai ter problema se você pergunta em português. Depois ela foi postdoc na Universidade de Houston, em Texas, e virou assistant professor, professor doutor na Rutgers University, e agora é professora na Universidade de Illinois, Indiana-Champaign. Ela fez pesquisa em monte de disciplinas diferentes ligadas à física hadrônica, como íons pesados, cálculos de rede da QCD, agora astrofísica, é isso que ela vai falar hoje. Como sempre, vai ter link da lista de presença. Se tem perguntas urgentes, pode pôr no chat, vai ensinar, vai ter sessão de perguntas depois. Jaki, it's all yours.
Obrigada. Agora eu vou falar em inglês, mas como o Giorgio falou, você pode perguntar em português também. And so anyways, I'm going to switch now. But thank you for having me here today. I'm excited to talk to you. And I'll be talking to you today about what we can learn from heavy neutron stars. And this essentially involves two different papers. This PRL we had right after the measurement of what could be potentially the heaviest neutron star. And then the second paper, that's a follow-up one that looks specifically on different types of phase transitions and how any measurements of heavy neutron stars could help us to understand better if there's a phase transition, what that looks like. Oops. Okay, so to get us started, I'm going to kind of walk us through a very general introduction to neutron stars and what we can learn from that. So, you know, bear with me if you're already an expert on this, but I figure there might be some young students that would like to know more. So anyways, if we have some sort of neutron star merger, this is actually black holes, but we can still get the same ideas that they would be rotating around each other. At this point, they're actually going to have some sort of tidal deformation of the neutron stars because of the gravitational pull between them. At some point, they merge So that's called the merger phase. And then you can see these gravitational waves that be propagating outwards in space. And eventually these gravitational waves are going to hit the Earth. You'll see in a second, and they'll hit basically LIGO and Virgo, and that's then possible to measure them. So the thing that's interesting about neutron stars and neutron star mergers is that they're combining all the fundamental forces in sort of one system. And that means that we have electromagnetism, you can have a large magnetic field, you can have visual signals, you have obviously gravity because you have gravitational waves that are emitted. There's the strong force, and that's the thing that I'm mostly interested in. And that's because you have nuclei, that is your degrees of freedom. Sometimes you have nucleons, and you might even have quarks as your degrees of freedom. It really depends on which layer of the neutron star that you're considering. And then the other thing that you have to reckon with is you also have the weak force. And so that means you can emit neutrinos, and you can also have strange decays. And from someone that has a heavy ion background, this is something that's kind of a new thing, because normally we always think about strangeness conservation. And so this is something else that you have to kind of keep in mind. If we think of like the different phases of a neutron star merger, we can also relate this to what you can imagine this gravitational wave to look like. So as we saw in the little video, initially the two neutron stars would be far apart from each other. And this is this kind of phase. This is called the in-spiral phase. We can think of the temperature as mostly equal to 0. It's not exactly 0, but it's very, very small compared to anything that we would think relevant for nuclear scales. And so at this point, the main thing of interest is seeing how deformed these two stars are as they inspire closer and closer together. And that is dependent on the equation of state. And so it's something we'll come back to later on this talk. But basically, if they become more or less deformed, that depends on how squishy or soft your equation of state is. As we go closer and they actually touch each other, that's the part where we say that that's actually the merger. This entire thing here is called a neutron star coalescence, and it's only when they're touching each other that is the merger phase. Now, kind of the issue there is, if you look at the signal to noise ratio, I don't have it shown here, is that the noise increases dramatically, actually even before they start touching, to the point where it's hard at this point in time to extract information of when they're actually merging. This is something that with future detectors they'll be able to do. However, when we're able to get that kind of information, it's quite interesting because it gets to very hot temperatures. It could actually be even similar to temperatures that are reached in like heavy ion collisions. So this could really be of interest to kind of both communities. And so there's different types of physics that you explore when they're actually touching each other. And you use some sort of like fluid dynamic simulation coupled to gravity to describe the dynamics of this. And then afterwards you have, this is the post-merger, and then after this you have the remnant, and that is whatever you're left with afterwards. And there's a lot of physics that can go into this remnant, because if it's really, really heavy, it might just go right to a black hole. You actually might have some sort of unstable, like this hypermassive neutron star that will eventually go to a black hole. It just takes a little bit of time to do it. Or you could have just a heavy neutron star that's produced. It depends a lot on your initial conditions, how heavy these original neutron stars are. At the moment, the only thing that we really have data on is this in spiral phase. That is something that can be extracted from the gravitational waveforms. And then the other kind of one data point that we have is what happens afterwards, is can you see a visual signal or not? And so as of yet, in all the mergers they've measured, they've never seen a visual signal after the merger, which seems to indicate that that's probably a black hole of whatever came out of it. Now, what I'm really interested in is how can we look inside a neutron star and see what's happening in this core of it? Because it's likely or possible that we could have quarks. And so we could have essentially at the very center of a neutron star some regime where quarks are deconfined. That would be quite exciting. And so kind of to see how that would look like by density is if you're at the outer surface, the outer crust of a neutron star, we certainly think of the degrees of freedom more like nuclei. And you would care about the ratio of protons and neutrons. Essentially, you'd expect them, as you go closer and closer to center, be more and more neutron rich and heavier until you reach a point where you cannot put another neutron inside your nuclei. It starts dripping out. and that's known as the neutron drip line. And so at that point, you have to understand how nuclei interact with nucleons. You can kind of see this in a picture form here. Now, if you continue getting to larger and larger densities or going closer to the center, you're continuing to squeeze your matter further. It's very, very dense. And you get these new phases that are called pasta phases. And that's basically like you get these kind of long strings of nucleons that fit together in weird ways, and they look like different pasta shapes. And if you continue to squeeze matter even beyond that, eventually you get to the point where you can describe this as liquid nuclear matter. And really what's going into that is n-body interactions, like 2-2 interaction, 3-3 interaction, these sort of interactions. And so the 2-2 interactions are pretty well understood. You know, you can use nuclear experiments to understand that. The 3-body interactions less so, and anything beyond that is really kind of a gray area. There's a lot of uncertainties there. But you could use different type of microscopic models to get at that physics. Now, at some point, you go beyond that. And it might be advantageous, for instance, to have Hyperon. So it's not just protons and neutrons, but you actually have strangeness that would be stable within, you know, another layer as you go closer and closer to the core. Or another possibility, or both, actually, you could have Hyperons and then you could have quarks. So you could have some sort of deconfined QCD matter at the very core of the neutron star. And that might have different types of phases. There's certainly the most uncertainty as you get closer to the center of a neutron star. So the way we kind of think of this is that we have to get to the extremely tiny scales, and to the point where you have to, you know, crack open the proton and see the quarks inside to connect to something and try and understand and interpret what's happening very, very far away. In fact, if you look at kind of the order of magnitude that you're dealing with, it's a similar order of magnitude away from like the human body in terms of smallness versus the distance away of, you know, the things that we're measuring in astrophysics. So just to kind of remind ourselves, although I think a lot of people looking at the list are already nuclear physicists, is what we're interested is like finding if we can have these deconfined quarks inside the center of a neutron star. And so just to remind ourselves is that we normally have them in some sort of bound states, like protons or neutrons. And we're always having to reckon with the issue of confinement. Like if you like try and pull them apart, you would actually get a quark-antiquark pair from the vacuum rather than deconfined quark matter. So only when you go to some sort of extremes can you get deconfined quarks. And so that's the idea, is getting extremely high densities to find deconfined quarks. And so one question that sometimes you hear is like, why don't we just calculate this in QCD? And unfortunately, that's just not possible. Gluons are tough and they self-interact and they make our lives very complicated. And so, you know, QCD trying to do something perturbatively, you could only use extremely high densities. And there definitely has been work done there, but the question is when it would be applicable, and that might not be applicable until like 40 times saturation density. And so this would be well beyond the regime that would be applicable to neutron stars. And so to get into the regime that you'd want, you'd have to somehow solve the Fermi sign problem. And it's not quite straightforward how to do that. And that it might well not be solved within my lifetime. And so this is something that we have to kind of use effective models and, you know, or you basically have one of two choices. You either use an effective model or you use some sort of functional form for your equation of state and try and extract what it is from the experiment. So let's talk a little bit about how that would work. The kind of bread and butter observable that you would have from a neutron star is the mass of the neutron star and its radius. And so let's kind of go through a simpler idea of how that would work, is that if I just take, you know, imagine that I have a sphere, that my neutron star is just a fluid, and I want to take a little cube from within the neutron star. And so if I think about what are the forces playing on there, I would have pulling me inwards, I have gravity, and pushing me outwards, I have pressure, right? And so those are the two things I have to reckon with. And so if I want to get the mass of a neutron star, that's pretty straightforward. I just have to integrate over the density and keep in mind that it's a sphere. So then you would have this differential equation here. The question is, what is this density and how do I get this? Well, the way that I can do that is I can just look at the gravitational force, right? And I have dp/dr, and basically I need my force over my area because I have this little fluid cell. And so I get this pressure equation, I get this mass equation. They're two coupled differential equations, and I can solve them. And so when I'm solving a differential equations, I need essentially my boundary conditions, I need an initial condition, and I need to know when to stop integrating. So my initial condition is something I'm putting in by hand. I pick a central energy density, and I just change that and vary that and get different solutions. And I'll get to that in a little bit in a second. But when I stop integrating is essentially the point where my pressure goes to zero. So if we think about like the surface of a neutron star, the point where I'm at that surface, that's when my pressure goes to zero. So then I just stop integrating, and then I know I've reached the radius and the mass of that neutron star. Now, of course, LISA isn't quite that simple. We also have corrections for general relativity, so we need to add those in. So it makes the equations slightly more complicated, but the same concept still works here, is that you have these two coupled differential equations, you solve them together, you stop integrating when the pressure goes to zero, and you're able to get a mass radius relationship for a specific initial condition. So then what are our variables? Well, essentially I can write this as pressure versus energy density, and this is an equation of state. And so the equation of state would encode all of that microscopic physics that we were talking about before, like what are the degrees of freedom, if it's quarks or if it's nucleons, it would encode how they interact. And so all of that information is getting fed into my equation of state, and then out it pops a certain mass radius relationship. And I'll show you what those look like in a minute. But that's kind of the main idea, is that we can learn a lot about what's inside a neutron star just knowing what is the mass and radius of many different neutron stars. And just so we're on the same page, because Giorgio mentioned that we might have some astrophysicists in the room, is that when I'm talking, I'm normally going to be talking about nuclear physics units and high energy units, so femtometers, MEVs over femtometers, although sometimes I do switch back and forth into like grams per centimeter cubed or something like that. So just to keep in mind what that would look like. So let's talk about how we actually get the mass radius relationship. So I mentioned a little bit about gravitational waves and how you get this information about the inspiral. Now, what do you do for observations? You would have NICER that's sitting right now on top of the International Space Station. And essentially what it does is it observes a pulsar. And so it would observe something like a hotspot on the pulsar. And so see this little orange thing here. And now over time, that hotspot's going to rotate around. And this provides them with information about the radius of the neutron star. So there's some modeling that goes into this because they need to figure out if they have 2 hotspots or 3 hotspots. I mean, there's always these kind of questions, but the longer they observe a neutron star, the more accurate that they can extract the radius of that neutron star. And so this is really the tricky thing. The mass is something that they can measure fairly precisely, but the radius is the hardest thing to get. Now, in terms of what we're going to learn for nuclear physics, it makes a big difference if we have a small neutron star versus a heavy neutron star. So you can see here, a typical neutron star is about 1.4 solar masses, and a heavy neutron star could be something like 2.1 solar masses. Now, if you remember, I said we had different initial conditions for our equation state that we put in, and we get a different mass radius relationship. Think of it like this, is if it's a light neutron star, our central density is also going to be a lot smaller. And so we're not going to be getting to large density. So it's most likely that whatever is inside of here is mostly nucleons, and we're not reaching quark degrees of freedom. However, if we have some sort of heavy star like this, like 2.1 solar masses, we can reach much larger densities inside the star. And these are the ones that are especially interesting and can give us a lot of interesting information about QCD and what's happening at these extremely large densities. And so, in fact, this was something J0740, you'll probably be seeing on the slides. This is a recent measurement that just came out this summer from the NICER collaboration. And as of today, this is the heaviest neutron star that we have a radius measurement for. So that's extremely exciting. And from talking to some of the people in NICER, it looks like over time we might even get better shrinking in those bands, the posteriors from them, which will be really exciting and help to constrain equation of state much more. So how does this actually look like? I kind of talked to you in general terms about this, but let's use an example of an equation of state. So here you have your pressure versus your energy density. And if we just have nucleons and leptons, this is something that you could think of called a harder equation of state. That means it just increases, the pressure increases a lot with the energy density. And so if you have a harder equation of state, it generally leads to a more massive star. So you can think of it like this: your pressure is pushing a lot outwards, and you're going to get a larger star at the end of the day. If you start adding new degrees of freedom, for instance, let's say that you don't just have nuclei and leptons, but you add in hyperons. When you add in that new degree of freedom, it softens your equation of state. It means that you change the pressure less when you change your energy density. And generally that leads to a softer star. Now, it's a bit more complicated than that because there's a lot of different ingredients that go into these models. It depends on interaction terms between different particles, but that's kind of the general idea, is that you have this softer equation state that leads to a smaller star and a harder one that leads to a heavier star. So then the question is, how could I actually distinguish something that has a quark core like this, or if I had something with nucleons inside? Now, what we can do is we can turn to the speed of sound, and I'll get to that more and give you explicit examples in a second. But the speed of sound is just dp/e, so how much the pressure changes with energy density. And if I were to just use a nucleonic equation of state, don't put any hyperons, don't put any quarks, and I kept calculating larger densities, I would see that it basically kind of goes very smoothly up to the causal limit. So when the speed of sound goes to the speed of light, and it actually would reach one and surpass it at some large baryon density. So that's a bit troublesome. And so we think we probably need other degrees of freedom. Now, at a quark core, you might get something, depending on how you transition. If you have a crossover first order phase transition into quarks, you might get something like a bump in your speed of sound that goes up very high, almost to the causal limit, but then softens again, right? Because remember, when you added those new degrees of freedom, it can bring down your equation of state. It depends like how big of a bump and where it is. All of this depends on the new degrees of freedom you're adding. If you're adding hyperons versus quarks, it depends on the interaction. There's a lot of sort of uncertainty that goes in there, but the general idea of having some sort of bump is coming most likely from quarks if it's a large bump. So to kind of see that more explicitly, there's two different kind of ways we can think about what would happen if we have quarks inside a neutron star. Now, the easiest conceptual way is just to say, okay, there's a very clear phase transition. And so when you have like a first order phase transition where in this case, there'd be one very fixed density that you're going to do your transition at, basically what happens is you could have your speed of sound, it goes up, and then it has a long flat regime across baryon density where your speed of sound is 0, and then you go up again and you have your speed of sound, and eventually you go to 1/3 at really, really high densities. And so this would be a first order phase transition, and there are some clear signals for that, but we'll talk about that later on. But let's first focus on something that might not be as clear. What happens if we have a crossover phase transition? And so that means that, just to remind you that a crossover would happen at kind of a wide range of densities. And so you could see something where it's a much smoother transition, and you could have something where you have a bump, and then you transition kind of smoothly into quarks afterwards. Now, in this case, and what happened originally in the field is that was done mostly just doing this phenomenologically. But I will discuss now, I think there's been a lot of progress made to argue that this bump could be really a thing, and there's actually some nuclear physics motivation for that too, which I'll get in the next few slides. So kind of see what is the physical motivation for this potential bump in the speed of sound squared that goes up to the causal limit. One of the arguments would be something called quarkionic matter. This was a paper from Larry and Sanjay a few years ago. And essentially what they do is they put in quarkionic matter and they get this really large bump. And so after the point where you transition, you have quarks here. And I've actually heard Larry call this like an unphased transition when this happens. Now, another potential model that has this would be the QHC19. This is from Gordon and Kojo and some of the other people in Japan. And so the idea here is that you would have, you know, some sort of microscopic model down here, and then you have an NJL phase up here. And so from what I understand, in terms of where this peak is coming in, it might be some sort of percolation phase that's kind of giving them this peak here as they go in the speed of sound up to larger densities. And then you definitely have quarks up here. And then another sort of model that gets this, but doesn't have quite such dramatic creaks, would be something with Hyperons. And so this would be an example from the chiral mean field model. And essentially you get these little tiny sharper peaks that are coming on when you have different Hyperon degrees of freedom that are switching on. Now, this little kind of sharp dip here is your phase transition. So I believe this is just Hyperonic degrees of freedom. And above this is when you have your quark degrees of freedom. And there's also some other more theoretical work that they haven't yet had numerical calculations yet, but some other explanations of why you could have a large bump in your speed of sound. You could have some sort of coupling between your O4 chiral field, phi, and a W mu meson. And so basically you have some sort of omega condensate that's formed. And what really causes this peak is that you have this mass change of the omega meson. And so you get basically it changes mass and it causes a spike in the speed of sound. And then the other thing that you could have, and some arguments were made, is that when you switch from a broken chiral symmetry phase into a gap Fermi surface, that this would also cause this kind of like bump in the speed of sound. But right now, these are both pretty theoretical and they need to be put into models to see like what is the order of magnitude of this, where this would happen. So unfortunately, I don't have any plots for you on those two right now. Now, to see what a speed of sound looks like from a lot of nuclear physics models, we kind of compiled a bunch of them together, and you can see a lot of nice examples here. And so you can see that the ones with Hyperons have these kind of like spiky peaks in them. You can have some sort of smoother bumps. This is just, you know, from an NJL model. And you can get a lot with first order phase transitions here, where you can see that the speed of sound is going to zero. And then just as a comparison, you can see the slide, which is just nucleons, protons, electrons. They might have other leptons, I'm not sure off the top of my head, but the point is that it just goes straight up, and at some point it becomes acausal. And so it looks rather tame in compared to everything else. So then the question is, well, okay, great. So those are the models, and you can calculate your model. But what about actual data? Is once, you know, we have these observations, what are those telling us? And can we eliminate certain models? And so what is the data telling us? Well, the kind of issue is we only have so much data, and they're still rather large. You can't really say that they're error bars, but you would say more they're posteriors from their analysis they extracted. But essentially, we have three real points as of today. And so there's J0030. So NICER had measured a lighter neutron star, this pulsar here. And then you have J0740. So this is the heavy neutron star that I told you about at the beginning, that they recently measured and came out just this summer. And then you have JW170817, which is the very first neutron star merger, where they had a very clean kilonova signature. You know for sure there were neutron stars. And you also can, essentially from the tidal deformability, there's a way to extract the mass radius relationship here. So the idea is, and just to make this a little clearer, is this green and brown bands are from two different separate collaborations. So it's the exact same data, but there's different methods to extract what the mass radius relationship is. So in principle, you probably want to take your wider error band into account on these cases. And so if you see this, you can see, well, maybe in a mass radius sequence could look like this, maybe it could look like this. We expect that you should have here at this regime the overlap, right? So this is kind of the outer edge on the right, and this looks like it's kind of like the left edge here, because it should fit within the whole band. And then you see up here, we have question marks. So this was some mystery object that was measured. I'll talk about this in a second. And this was another mystery object, but it's a lot more massive. So people generally think that that might be a black hole. I just haven't seen nearly as much published on this. So there's more question marks here. And we'll see if we get more information. Now, if we go back here and take only the stuff that doesn't have question marks, and imagine that you did a statistical analysis and tried to extract the speed of sound, then here's kind of what you have today. Is you imagine that the speed of sound is quite low at low densities. That's very consistent with the lower density regime of the equation of state. And then at some point, you expect a very steep increase in your speed of sound. Now, I wouldn't take this part here that's kind of empty too seriously, but I would take this steep increase here quite seriously. And so it seems like there's some convincing evidence that at least even with these wide bands today, that we have a pretty sharp increase in our speed of sound. And that could be happening around 2 times saturation density. Maybe it's happening at a little bit larger densities as well. But there does seem to be this preference here. So then the question is, well, what happens? What about this heavier object? And what could we learn from there? So like I said, there was this mystery object. Essentially what happened last summer is a black hole and something else merged together. It was either a neutron star or a black hole. Whatever it was, it's either a super, super heavy neutron star or a super, super light black hole. And so it's in this weird gap where we don't know what it is. It was around 2.5 solar masses to 2.67 solar masses. And so there's been a lot of thoughts on what that could be. Now, the second this hit the archive, you can imagine the theorists got very excited and they started putting out papers right away. And some of the thoughts could be that it was a spinning neutron star. It might be a primordial black hole. It could just be a super fast pulsar. There might be some sort of exotic degrees of freedom in there. We don't know. And it's hard when you have some sort of collision like this, when you have a really, really heavy, massive black hole, because it kind of engulfs all the signals. And it means that it makes it much harder to actually know if that companion was a neutron star or not. So the collaboration then tries to do an analysis and argue one way or another. And so basically they convinced themselves that it should not be a neutron star black hole merger. Basically, they said comparisons between the secondary mass and several current estimates of the maximum neutron star mass suggest that GW 190814 is unlikely to originate in a neutron star black hole coalescence. So you can see they're hinging their argument basically on the neutron star equation of state. And they argue that from what they did in their analysis and the assumptions they made about the equation of state, that you can't get a maximum mass large enough to 2.5 solar mass. And so that was unlikely. So to kind of talk you through is that they found tension between this larger maximum mass and constraints that they have on the radius and the tidal deformability. So we're going to get into that quite a bit. The other kind of arguments they have are not quite as strong. One is that they don't have a visual component. So a black hole would be dark, but there's other reasons why you might not have a visual component. In fact, if it's something very far away, it's hard to get a visual signal. It could be that, if you have some sort of signal, it's just pointing in the wrong direction. There's a lot of reasons. Also, it's colliding with a very, very large black hole. This can also kind of engulf the visual signal. So there's a lot of reasons why that might not happen. Another argument is basically galactic population in terms of statistics, but there could always be some sort of bias in terms of where you're looking or how we observe things. So this isn't quite as strong either. And then the other kind of issue, and it's not so much an argument against, it's more that you could not measure the spin. And again, this is because if you have a companion that's a very massive black hole, it just makes it hard to measure things. So we don't know if it was spinning or not is the idea. But let's really address this one, because this is the one that, if you cannot create an equation of state that has a neutron star massive enough to be around 2.5 solar masses, then it's a no-go, right? So let's see how correct this is. Well, what did they do to get the equation of state? Basically, they put in some, known constraints. They put in the mass radius relationship. This was done from that I was shown before. They also put in that the speed of sound has to be causal. That's all good. And they use the adiabatic index, which is fine. Now, the kind of tricky thing here is they have to put in some sort of expansion when they do this. And when you make that assumption, basically it limits you to only a certain regime in the equation of state that you can use. So when they check this, there's some modeling assumptions that go into if this equation of state would work or not. Now, to investigate this, it really helps to have some sort of collaboration. So this was a collaboration between us nuclear physicists, Veronica Dexheimer at Kent State, my PhD student, Travis Dorr, and then our gravity people. So this is Nico Yunus and Hong Tian, his PhD student. And so we decided, like, let's do something much more general. Let's create our own equations of state that try and build in a lot of the structure that I showed you before in the speed of sounds. Like we have bumps, we have kinks, we have first order phase transitions. And so we came up with an algorithm that could put in all of this structure into the speed of sound. Now, the next thing we do is we don't want to worry about the low density regime. That comes from a lot of modeling on the low energy nuclear physics side. And so we said, well, let's just have, other people do the work for us there. And so we took some low density equations of state and tested those. So we just kind of varied those a little bit and used what other people have done. And so we put then the functional forms above saturation density, or normally like 1.5 times saturation density or above. And we also could, in principle, put in and force this to go to the PQCD limit. To be honest, we found that, after you get past the density, the central density, anything that's at like 4 times saturation density did not affect our results. So why do we start from the speed of sound? Well, I kind of covered some of this already, but it is kind of interesting to look at this formula. If you take at 0 temperatures, the susceptibility, so the dp, d mu b, the second order, you find that directly connects to your speed of sound. So you can basically, just thermodynamically, this pops out. Your speed of sound is equal to your baryon density divided by mu b times chi. And so it kind of connects more directly to stuff with phase transitions. It seemed to make a lot of sense to me to use this as a starting point. And also because if you have a first order phase transition, you expect some sort of plateau where your speed of sound goes to 0 for some regime. Whereas if you have a second order phase transition, your chi2 diverges and you can get a spike of speed of sound down to 0. And as we were seeing before, we get these kind of peaks and bumps. Probably from some sort of crossover, but it could be some other reasons as well. So let's build some equations of state and see what happens. So one thing that we learned very quickly on is if we put in a large bump into our speed of sound, we were quite easily able to get up to 2.5 solar masses. So we put in a bump, and we do find it's not just generic. We can't just put a bump and it works, but we need to have a certain width to it. And if we make it wide enough, as you can see here, like this wide bump here, it does crank up the maximum mass enough to give you 2.5 solar masses. And so the idea is you need a bump and you need a pretty substantial bump, but that will give you the 2.5 solar masses. Now, it does depend at what density this bump is turning on. So you can think of it as like, what density are we transitioning into maybe quark degrees of freedom? And in this case, you can see that if we have a transition that's happening at very low densities, it makes our equation of state very stiff, and it makes our stars very fluffy. And so essentially what happens is you get a large radius here, and so you have a large mass too as well, but it still fits within all the known constraints. Now, I can also push that phase transition to higher densities, and that will work to a point. But at some point, it doesn't give you a large enough maximum mass. So it would still be consistent with J0740, but it wouldn't be enough if you if this bump at very large densities to get up to 2.5 solar masses. So it depends, first of all, how wide your bump is and where exactly your bump is located. Now, you could kind of ask, like, well, can we kind of do some interplay with that and still get up to a large enough maximum mass? And the answer is yes. So for instance, I could take a very narrow bump at low densities and I still get to 2.5 solar masses. If I push that bump to larger and larger densities, then I basically need my speed of sound to stay at the causal limit for a longer and longer time. But I can pretty much get up to 2.5 solar masses. So we can definitely show that it's possible to get up to 2.5 solar masses. There's nothing special about that, or nothing that, at least from the functional forms of speed of sound, that prohibits producing neutron stars that large. And in fact, we generated many equations of state to do and look into exactly that. And so you can see it looks kind of chaotic, but the point is that there's many different equations of state that can produce something with 2.5 solar masses. So what happened? Well, we looked at their posteriors from their equation of state. So these are this pink band is what they extracted for their pressure versus energy density. And these are the equations of state that we generated. And so all of our equations of state fit within the no constraints, but you can see they definitely don't match with their posterior of the pressure versus energy density. So why was this not included in their model? Well, what ended up happening is their equations of state were not flexible enough. And it was interesting. It was something weird. Is they could fit to nuclear equations of state, and while it looks like the chi-squared fit was not so bad, once you actually plotted the adiabatic index, it has large deviations in a kind of small window and density. However, those deviations matter, and those deviations can actually push you within or out of the constraints. So to see this maybe more clearly, this kind of bump here is from one of our equations of state with the structure, with a large peak. And you can see if I plot it here, that fits all the known mass radius relationship. However, if I try and fit one of their spectral equations of state to that and use the same priors as them and everything like that, I end up not getting to a large enough maximum mass. This line here is supposed to be reproducing this dashed line here, and it clearly does not. And so this was kind of the systematic problem, is the formula that they were using to create equations of state was not flexible enough to encode all of these bumps and kinks and all the structure that we do believe is there from nuclear physics. So how can we actually say if this really heavy thing is a neutron star or not? And for that, we need to look more into the inspiral and this thing called the tidal deformability I talked about before. So basically, as two objects approach each other, they're deformed, they're elongated, and this is something where you can extract equation of state information from. Now, for black holes, that's not the case. They're not deformed whatsoever. The tidal deformability is identically equal to 0. For light neutron stars, they're squishier, so they can be deformed quite a bit. However, once you get to heavy neutron stars, they're very compact, and they have a very small tidal deformability. So in fact, to the point where it could be very difficult to tell if something is a black hole or if it's just a very, very heavy neutron star. And to give you an idea, we actually tried to extract the tidal deformability to see if that was within the precision of LIGO and Virgo. Now, you can see here from, if we take 2.5 solar masses, that our range in the tidal deformability was from, I think the lightest one we had was like 2 or 2.5, going up to 20. However, if you see the actual precision of the tidal deformability that they're able to measure, it's only at the order of magnitude of like 100 to 400. So essentially, the precision of the experiments are at an order of magnitude larger than you'd want to be able to distinguish if a very heavy neutron star is a black hole or not. So they just can't say at this point in time. Now, let's go back to, that was all about crossovers. Let's talk about first order phase transitions briefly. Now, there's different ways that this can appear, but if you have a very strong first order phase transition, essentially you can create something called a mass twin. And so this would look like the following: is you have your mass radius relationship. These are different neutron stars. At some point, you add in a larger central density, and you have this unstable branch in red. And then when you have first order phase transition line, you can actually have a second stable branch here. That means that you could measure a star here and a star here. They'd have the same mass, but very, very different radii. And so you can either get a high disconnected twin that this happens at a large mass, a low disconnected twin when this happens at a lighter mass. You can actually get something called a connected twin, which is when they don't have an unstable branch in between. However, you can see here, I could essentially measure something with a mass here, and maybe this mass is like an epsilon larger, but it's such a small difference that observationally, you'd never be able to tell the difference between a disconnected twin and a connected twin. Other thing that can happen, and this is normally when your first order phase transition is not super large, is you can get a kinky sequence, which is when you go like this, and then you have this kink, and then you go over. Now, a regular sequence would look much smoother, but you can see, remember those large arrow bands we had before, it might be very hard to observe that, unfortunately. So we wanted to understand more how a phase transition would affect our mass radius sequence. So we did something quite simple, is we just took exactly the same low density regime. You can see up to here, we put it so it hit the very, very bottom of the bands of J0740. And we wanted to see if we played with the width of the phase transition. So basically, if it's a strong one or weak one, how that would affect the mass radius sequence. And so if we put in a very weak first order phase transition, like it's almost nothing, then you can see it looks like a very standard mass radius sequence, and it's rather boring. And in fact, I don't think there's any way that you could easily observe that at all. If you continue to like crank up the width of the phase transition, eventually you turn into this kinky sequence here, where it starts bending over. But that still might be kind of hard to observe that there really is a first order phase transition there. But if you continue to have a much stronger phase transition like this light green long dashed one here, you see that that flattens out, and oops, that really might look like mass twins. And that would be something that's an observed, something that you can observe. And if you continue cranking up even further, that the separation here, the unstable branch, this is a stable branch, this is the stable branch, is going to be much larger. And if you have a really, really large phase transition, it could be very, very different. And that is something that one could probably easily measure. Now, if you continue cranking up beyond that, at some point, there's just not going to have a second stable branch. And so that's what this like light brown line is. It just only has this one branch here. What else can you do? Well, you could also change the location of the phase transition. And it has a different sort of effect, is if you have your phase transition at low densities, you're going to have something like this, where you can have kind of a long second stable branch. But if you continue to push that up to higher and higher densities, you're going to cut off your second stable branch, which is going to be much harder to observe. And then eventually you're going to kill off your second stable branch altogether. So you could have a first order phase transition that basically leads to no observable consequences. And that's kind of hard to measure. Now, is it possible to have a first order phase transition and still get up to something very heavy like 2.5 solar masses? Yes, the answer is, but it's going to be very hard to observe that, because you can see that this mostly looks like, you know, just one stable branch. This is just this small little kink here, which would be hard to see. And this one could look like a connected twin, but really the observable effect is quite small. So you could have a first order phase transition there. There's nothing eliminating that possibility, but it looks like it would be hard to actually see it. Now, I think I'm almost out of time, but I do want to mention briefly that if you go to neutron star mergers, you kind of are putting yourself on the different axes of the phase diagram. Everything I've talked about here was for 0 temperature neutron stars, but if you go to finite temperature, if you go to neutron star mergers, you get into this finite temperature regime. And so just to kind of remind you, this is this merger phase right here. And the saturation density, you could get to like 1 to 8 times saturation density and up to like 100 MeV in temperature. Now, it's a little bit different for those with a heavy ion background in terms of the axis of the phase diagram. You can look at this work from Veronica, where she compares like symmetric matter versus asymmetric matter. So neutron stars have many more neutrons than protons, versus heavy ion collisions where it's almost an equal amount. And while it's not a massive difference, it does mean that if you have a first order phase transition, it can shift its location to the point that, like, if in a heavy ion collision, it might have a phase transition or higher chemical potential, whereas for a neutron star, that could then shift it to a lower chemical potential where you're actually seeing that phase transition. There's also some observable effects in the actual numerical simulations, that if you have quarks inside or not. There's a little YouTube video. Let's see if I can like go speed up a little bit so you can see. You can see basically on the left, they show the quark phase. And so you can see that's kind of more in the center, but there's also some in the ring on the outside versus the entire simulation. Now, there are some potential observable effects there within the merger itself. This would be basically, right now they cannot measure this, but this is something with future detectors that's likely that you could actually measure, is that you could shift your frequency peak to a different value. There's also some delayed phase transition that you could go to. And there's also another thing that you could look into is for hadronic versus quark degrees of freedom, you change basically your ring down signal. It'll affect, what that looks like and how you go into a black hole. But right now, these are more speculative because, again, we just don't have the information with the current detectors. But, this is something that's going to come in about. And I think kind of one thing that needs to be explored that hasn't been explored yet, and it connects to heavy ions, is how do you explore this stuff out of equilibrium? So far, all the simulations I showed you were with ideal hydrodynamics coupled to GR, but it could very well be that there needs to be viscosity in this as well. And so we think there's a lot of similarities between heavy ion collisions and neutron star mergers. You can see here, this is a comparison at Hadi's energy versus a neutron star merger at the top. This is a Hadi simulation at the bottom. So we're all using fluid dynamics here, but the question of what kind of goes into this. So nominally, we think that if we have something that's far from equilibrium, that's going to affect our pass through the phase diagram, and the farther we are from equilibrium, that's going to affect this passage through the phase diagram much, much more. And this is some recent work from my students that kind of showed this exploring. This is at higher temperatures, but you should have the same effect also for neutron star mergers. The wrong direction. And so there has been some really cool work from the group at Washington University, from Mark Alfred, looking into the effects of how bulk viscosity would appear in neutron star mergers. And in fact, this depends on a lot of factors like the degrees of freedom. If you're talking about nucleons versus hyperons, and then for quarks, there's a lot of question marks there. Depends on your temperature and density. But you can see that this is a new way to probe what are the degrees of freedom within a neutron star. And so we did a kind of back of the envelope approach to this. Is we did the simulations and then put the bulk viscosity kind of on top of that, and just to see what the order of magnitude of what the bulk pressure would look like in neutron star mergers, and then compare that to regular simulations within heavy ion collisions. And so this was basically based off of the Duke-Bayesian tune of getting the bulk pressure over the energy plus pressure compared to what we got out of the neutron star merger. And you can see that while this is kind of at the low end here for the neutron star merger, it's still pretty close. It's not crazy far off of what we're getting from heavy ion collisions. So it could be that, once we put in viscosity, that this is a new way to understand if we have quarks, degrees of freedom, or something else inside there. And so anyways, I think I'm going to just skip ahead because we're pretty much out of time. So I was just going to cover a little bit more on the heavy ion side. But just to kind of summarize, is that if we do have some sort of first order phase transition, there'd be a number of consequences. You could have twin stars, you might have gravitational wave signals, or it would affect your remnants even as well. If you have some sort of bump, this would have different types of consequences. And especially if we understand better about these heavy neutron stars, this will really give us insight into if there's some sort of bump there, and exactly where that's occurring and what is causing it. And also the other kind of thing that I was discussing is that I think now with this possibility of putting viscosity into the calculations of neutron star mergers, this is a new way to see if we have quark degrees of freedom or not. And so that should be something interesting to explore down the road. So with that, thank you very much for having me here.
Thank you very, very much for this great talk. Preguntas, questions? Raise your hand, and if I don't see you, or if you don't see you, just speak up. I have a question to start. Sure. Since I remember that for a very long time, there was a big problem that in computer code, supernovas didn't explode. Mm-hmm. I mean, there is this back of the envelope model of how supernovas explode, but if you actually put it in the computer, you don't get an explosion. Mm-hmm. So is that a constraint on the equation of state?
I know people are talking about this, right? Because you would have to put in some sort of finite temperature equation of state. Yeah. In terms of where they are, I just don't unfortunately know enough about their simulations. Like an obvious question that I would have is how they're handling anything with viscosity in their simulations. So one thing that we realized talking to Elias Most is that when you have an ideal system, it's kind of strange the way they create temperature. Because if you have like two neutron star mergers like in spiraling, and then they collide with each other. Basically, you're starting at 0 temperature and then somehow magically getting up to high temperatures. So what they do in their numerical simulations is they have a shock wave, and that's how you create temperature. But when you think of normal simulations, you would have viscosity that creates temperature. And so I do wonder how much, not having viscosity in their models is affecting things, but I don't know enough to say really.
Okay, fair enough. Fair enough. It's further questions? Anybody? If not, I mean, when you mentioned HBT, you mentioned it's HBT in heavy ions, right?
Yeah, exactly.
Yeah. HBT with neutron stars would be great, but
that would be great. I know. Yeah, there's a lot of things that, like, if you could somehow observe it, would be awesome in neutron stars. It's just, the problem is you're on Earth and you can only see whatever's pointing in your direction. And so you could definitely think of like observables that, if you could measure, would be amazing.
Okay.
But I'm just not sure how you'd get that information just from us on Earth. That would need some clever astronomers to do it.
Fair enough. Questions?
Hi. Maybe Jackie could talk a bit about the last slides on the heavy ions that should.
Oh, sure. Sure. Yeah, I can go back. Let's see. Where am I going here? Yeah, so the one thing that I had here basically is talking about the fixed target experiment in heavy ions. And so there's still a lot of the same questions that you see in neutron stars, like if there's quark degrees of freedom or not, are also getting asked there. So if you look at the phase diagram, are these fixed target experiments going to high enough temperatures and densities that they're above this phase transition line or below? And that's not quite clear. And so the kind of issue that's been going around, especially in the nuclear astro community, is there was a 20-year-old paper from Danielovich, Roy Lacey, and somebody else, I don't know the third author, where they took a transport model and then tried to extract they just changed a few variables and tried to extract the equation of state. And they did this from V1 and V2 in one centrality at different beam energies. And so they have this band here. And now what's happened in the field of nuclear astrophysics is they still use this 20-year-old data band and constrain their models. And so they say, oh, this doesn't fit the heavy ion constraint. Look, I can't use these lines because the pressure versus density doesn't fit heavy ions. And so I think this is pretty problematic. If you think about this, because it's not a systematic check, it's not a Bayesian analysis. They've never put in quark degrees of freedom. I mean, and it's nothing against also. I think what they did was a very cool idea, 20 years ago. But I think that we need to actually, as a field, kind of say that's not really what our standard is nowadays. So I kind of go over what we are doing nowadays. And so one of the things that's an issue at the low beam energies is that everything depends on everything. And so there was this nice paper from Hannah some years ago where she found that if you look at V2, right, at just very low beam energies, it depends on your initial conditions primarily. So that's the biggest factor. Then a little bit on the hydro itself and also on hadronic rescattering. So if you're getting your initial condition wrong or you have poor assumptions there, you're kind of out of luck because that's where it's giving you most of your V2, but it is affected by other things as well. And we could put in a lot more into the hydro, right? So this is an ideal hydro code. This doesn't have, the full 4D equation of state. It doesn't have diffusion. It doesn't have a critical point. It doesn't have, any sort of criticality in there. And so, there's a lot of things that I think on the theory end is just it's not in the models right now that should be. But even if you take that, if you take some sort of simplistic hydro and then compared it to the data, you could see that actually there is a preference for quark degrees of freedom, even at these low beam energies. So this was some work by Marcus and Spielis not that long ago, where they found that if you put in, I think it was the chiral mean field model, it actually works pretty well compared to the data. Whereas Hannah had this really nice paper using SMASH, and it has all the bells and whistles, everything up to date, and it doesn't fit nowadays we have a bazillion data points from SMASH, right? and we have a bazillion data points from Hades, and it doesn't match the data. And so to say that we only have hadronic degrees of freedom at these low beam energies is just, you can't say that.
I love it how you have the back of the envelope model and it fits everything, and then you have the model with every bell and whistle and it doesn't. It's the history of physics.
Right, right. And so, I mean, I think as a field, we kind of have to be like, hey, stop using this thing from 20 years ago. We don't know the answer here. That's why FAIR is being built. That's why NICA is being built. And I think we just need to, if people start using this data, we have to say, stop using it. And so I think as a field, we need to make that very clear to outsiders that we don't know the equation of state at large baryon densities. But there was one cool thing, and I think this will help us to maybe get somewhere, is Agnieszka has done some really nice work with putting in potentials into SMASH. And so you can kind of mimic phase transitions with this. Now, they don't have partonic degrees of freedom, but at least could help you to see what's the effect of a first order phase transition in some sort of smashing. And I think this has a lot of cool potential that is kind of moving beyond these simplistic approaches. So I think that was it.
It becomes more like a Vlasov equation than a Boltzmann equation.
Yeah. Yeah.
I see. Yeah.
Mm-hmm. And so I think you could take this model and actually I've been talking to her and Dima Ilyushenko a little bit about could you take this and take constraints from neutron stars and put it into heavy ions and vice versa. I think there's some really cool potential there that hasn't been explored. Cool. But I have a feeling it's not going to look like this simple band that we see from what happened 20 years ago.
Further questions? If not, well, first of all, let me thank you very, very, very much.
You're welcome.
Todo mundo gostou. And do you want to stop?